These are the notes for circular speed. I hope you have your worksheet so that you can read it, because I don't know that you'll be able to read it on the camera. But hopefully you can at least see the picture. We have a merry-go-round, the kind that they have at the park, that you hold on to the rail and somebody pushes it around. So that's what we're dealing with. Dad likes to take Junior to the park, and there the father likes to push his son on the merry-go-round until he gets dizzy, holding onto a rail and standing 8 feet from its center. So if you can see over here on the picture, they've got Dad marked 8 feet from the center. Dad runs 3/4 of the way around the merry-go-round before he lets go. And it takes him 3 seconds to do that. Junior rides on the merry-go-round 5 feet from the center. So the first question is a pretty easy one. How many degrees is 3/4 of a revolution? Well, first of all, how many degrees are in a full revolution? One revolution is 360 degrees. So 3/4 of a revolution is 270 degrees. So that's how many degrees Dad runs before he lets go. So the question is, what distance does Dad run during this 3-second interval? Well, Dad is running along the outside of the circle, which would be circumference. Remember, we find circumference is 2 pi r. But in this case, he's not running the entire circle, so we're going to do 2 pi r times 3/4, which is 2 times pi. Dad's radius is 8 times 3/4. Now remember, we discussed leaving things in terms of pi to avoid decimals. So what that means is I'm not actually going to multiply by 3.14. I'm just going to leave the symbol pi in my problem. So if I'm going to do that in my calculator, if you'd like to do that in your calculator, I'm going to do 2 times 8 times 3/4. And I realize you can do this in your head. I just want to make sure that you know how to do it in your calculator. And I get 12, but I left out this pi, so I have to attach it right here, 12 pi. Now, that's the distance he runs in the 3-second interval, 12 pi feet. In feet per second, what is his average speed? Well, if he's running 12 pi feet in 3 seconds, then his average speed would be 4 pi feet per second. And then just divide that out to get his average speed. Now the question is Junior moving at the same speed? Well, if I plug Junior's information into this same problem, so 2 pi r times 3/4, but we'll use Junior's radius, 2 pi times 5, you get 15 pi over 2. That's how far he's going. And then of course we still have to divide that by 3, which is the same as multiplying by 1/3. And I get 15 pi over 6 feet per second. So obviously it's not the same. Dad's moving at 4 pi feet per second, and Junior is moving at 15 pi feet per second. So it's obviously not the same. So the question is just to discuss the difference between the two different types of speed. Because if you look at it, Junior is still traveling 270 degrees in the same 3 seconds, isn't he? If we looked at this picture, if Dad and Junior are both rotating around, they're both traveling 270 degrees in the same 3 seconds. But the distance that they're actually traveling is different. I'm going to go ahead and multiply these two out so that you can see a distance that you understand. So in this case, it looks like Dad's running about 13.6 feet per second. And Junior is traveling about 7.85 feet per second. So that just kind of gives us an idea of something we might understand a little bit better. Now, most of the time we like to leave things in terms of pi because it keeps us away from nasty decimals. But the reason that they're different is because one is measuring angular velocity. Velocity is speed, but usually includes direction as well. So for example, if I was to drive my car through the parking lot backwards at 20 miles an hour, 20 miles an hour is my speed, negative 20 would be my velocity, because velocity includes direction. Angular velocity is how fast something is rotating. It's how fast it rotates or spins, or even how fast an angle opens. And angular velocity is going to be measured in, for example, degrees per second, or radians per minute, or one that we're really familiar with, revolutions per minute. We usually call that RPMs. It's some sort of angle measurement over a time measurement. So I'm going to write that. It should be an angle over time. And remember, we discovered, or a rotation over time. We discovered a couple of days ago that there's a new angle measurement called radians that we can use, not just degrees. So that's the units that you could find angular velocity in. So when you start to read a problem and you see one of these, you know you're dealing with angular velocity. Linear velocity is how fast something travels through open space. Now, linear implies to us line, but it doesn't have to be a straight line. So when Dad was traveling outside of the circle, he was running through space. So that's a linear measurement, even though it's not a straight line. Linear measurements are ones that we're kind of used to, like mph, or miles per hour, feet per second, meters per hour. Anything like that would measure linear velocity. So it's always going to be like a measurement on top, kilometers, miles, inches, feet, something that measures distance over time. Now we can relate these two speeds with a formula, and the formula is VL equals R times V theta. And you can look right over here. V theta is angular velocity, but notice it has to be in radians. So we're going to have to do some converting like we did yesterday. And VL is linear velocity. Now this particular formula, VL equals R V theta, you might see written as velocity equals radius times this funky W, which is a Greek letter omega, lowercase omega, which means it means angular velocity. So you might see it written either way. Okay, so let's try a problem. So at the top of the page, I have a circular saw blade with a 12-inch diameter, and it's spinning at a rate of 1,800 revolutions per minute. What is the blade's angular velocity in radians per minute? Well, I recognize revolutions as how fast something spins per minute, so this that they've given me is an angular velocity. I just need to convert that to radians. So I'm going to do 1,800 revolutions over 1 minute. I need to cancel revolutions. So I know that 1 revolution is 360 degrees. It's about the only conversion factor on revolutions I know. But I can, now that I'm in degrees, I can cancel degrees and go to radians. Now remember, radians doesn't have a label, so I'm going to put RAD in parentheses. And now I want to leave this in terms of pi as well. If you're going to plug it in your calculator, you just don't plug the pi in and you tack it on at the end. And this one's actually pretty easy because 180 goes into 360 twice. So I get 3,600 pi, and this is radians per minute. That's my angular velocity, and I'm now in radians, which means that I can use this formula from the other page, the linear velocity equals radius times v theta, because I am now in radians. So I want to find linear velocity. So this is the formula I'm going to use. I need to do my inches, my radius, but they gave me a diameter, so I have to half that. So I'm going to do VL equals 6 times 3,600 pi. Now, if I'm going to leave this in terms of pi, I get 21,600 pi inches per minute. Because this was 6 inches, remember radians doesn't have a label, so it was radians per minute, so now I'm in inches per minute. Now it says to convert this linear velocity to feet per second. So I have 21,600 pi inches over 1 minute. So we're just converting now. I need to go to feet. So 12 inches is 1 foot. That cancels my inches out. And then I need to go from minutes to seconds. So I know 1 minute is 60 seconds. Now you can just multiply straight across the top. Don't put the pi into the problem. Make sure you put the bottom pieces in parentheses. And I end up with 30 pi feet per second. And that's how you do circular speed and linear velocity.